So as we get into Module 4, we're taking a look at the topic of materials. Specifically, we're going to look at testing and selection and properties of the materials there. Now, an overview for this week, we're going to take a look at the selection of materials and the process used in fabrication. So that's something that we want to consider right there, is when we're thinking about the materials, not only how is it going to work well with our specific part or product, but how that is going to look in terms of the manufacturing and the fabrication utilizing those types of materials. So these are integral parts of the design of any type of machine component right here. Another thing to consider when we're talking about the material selection is the strength and rigidity. And these are traditionally factors that are considered in the selection process of that material. So we'll look at that and a couple other factors that tie into material selection throughout this module here. So within the module, we're going to talk about a couple different topics here. First, we're going to take a look at the tensile testing procedure, relate this back to some practical applications and some of the work that I've done. Take a look at stress strain, how those graphs tie into our tensile testing procedure and how we can get information and data from the graphs. Take a look at some high absorbing capacity, energy absorbing capacity, hardness tests, continuing on from what we talked about before, material strength properties, machinability, again talking about the manufacturing process and the different types of machinability of these various materials we may be selecting. And then we're going to compare a couple different types of metals, plastics, and composites and look at their material properties as well. And last, we'll take a look at the material selection charts and the process. Now, tying back to your textbook, this is covering Chapter 3, Sections 1 through 14 for this module. So for the first lecture here, our module 4.1, as we jump into this here, we're going to be taking a look at materials and now specifically taking a look at testing, stress, and strain are the topics we're going to cover within this first module, module 4.1. So we'll go through the tensile testing procedure, take a look at some practical applications, a few different projects that I have worked on in the past, and I'll tie in the tensile testing procedure for those, talk about data collection, the importance keeping track of your notes within that data and your data acquisition rates and all of the important parts within the testing process. Then the output of those processes there, we'll take a look at stress and strain and what we can infer from some of those graphs there. Then we'll talk a little bit about the energy absorbing capacity, some hardness tests, and work through some example problems as well. So topics and activities we'll cover within this module. We'll talk about those theories, key equations, a couple practical applications, and then get into some actual problem solving utilizing that theory and key equations that we discussed. So one thing that I do want to discuss right now are these live synchronous lectures. So this course is designated as a remote lecture, not an online class. This is meant to be the substitution for an in-person class. So you come to these live lectures on Tuesdays and Thursday mornings, and that's where you get the material. You'll take your notes from there, and that's what you're going to use to help you study, work on homework problems, prepare for exams, all of that. So this is a live synchronous lecture right here, and these lectures are mandatory. Now, I've had an increasing number of students recently that have been asking, hey, can I miss lecture and just watch the videos and everything you put up online? Now, this leads me into talking about these different modalities for the courses. This being a remote course and not an online course. So being a remote course, technically there's usually not any materials provided online on Blackboard. It's just these live synchronous lectures. I've decided to go above and beyond and give you guys some additional resources to help you study and help you learn the material better, but this is not something that you can use as a substitution for these live lectures. Now, at the beginning of the semester, you selected one of these modalities. So this right here is the remote modality right here, and this is a remote course here. So you need to attend these lectures. Now, the other thing I want to discuss with this is the fact that we are in a pandemic and this is COVID. So if you have extenuating circumstances, you're quarantined and you can't make it, please reach out to Student Health Services and make them aware of the situation. Reach out to Student Services and let them know as well. That way we can make the appropriate modifications and accommodations for you if you have that situation where you are affected by this pandemic and for some reason you're not able to attend these live lectures. But if that is not the case, then please realize that these are mandatory, and mandatory in the fact that don't just come in, turn on your camera, and go back to bed, but actually pay attention. There is material in the live lectures that it's not necessarily going to be covered in the pre-recorded videos that I have gone above and beyond to create for you guys. Now, I'd also reference you back here to this website right here, and this talks about these different instructional modes, the requirements for each of these modes right here related to classes within these. Now, I do teach online classes as well, but this is not one of them. This is a remote class, so again, these live synchronous lectures are mandatory. So a little bit of detail on what these are, and I'll leave this up for you guys to read through as well. But these, the at-home section, these are for seats with mixed courses that have been set aside for at-home students. So unless you have pre-designated as an at-home student, this does not apply for you. This, again, is what I want to focus on right here. This is a remote course, so this is indicating remote instruction. So these classes will have assigned meeting time and will meet live online instead of in person. So it's just the online version of an in-person class. So it's just these live lectures that you're getting, which would be the equivalent of having these lectures in class. So this is why I participate you guys to have this back and forth conversation during our live lectures so that you can get that feel of being in person as if we weren't in the pandemic, we didn't have this remote course. Now, depending on the course design, these remote classes will include a range of instruction from examples, lectures, group discussions, activities, demonstrations. So this is kind of the university's general statement, and this is the same for any in-person class that you would have as well. You know, maybe we'll be sitting there having group discussions instead of just a lecture, things of that nature, back and forth conversations. But again, this is the modality for this course. This is a live lecture remote course right here. This is not an online course, which you can see the description of down below. And if you click on the link that I put on the previous slide, you can go through and read in detail how the university defines these different modalities for these. So again, just want to reinforce that this is a remote course. The lectures are mandatory. You need to show up in person, be paying attention, be attentive during these live lectures, and not just depend upon the additional resources that I have decided to go above and beyond to provide you guys with these pre-recorded lectures, my lecture slides, all the different modules and everything else there. Those are not part of a remote course. I've just decided to give you guys those as additional resources in helping you study and learn the material, and not as a substitution for these live lectures. So as we begin Module 4, this relates to Chapter 3 in our textbook, covering the topic of materials. So as we talk about materials, I want to discuss a few different things here. So things that we should have learned in some previous courses right here and in previous modules within this course here are mechanical behavior. So we've talked about this briefly about mechanical behavior of material, and how we've kind of quantified this is looking at these stress-strain curves. Now with these stress-strain curves, we've already gone through a little bit, and we'll go into a little bit more detail within this module of how we develop these stress-strain curves. So if we're talking about doing material testing and taking a look at material behavior for various types of material, we can talk back to, let's just say, a tensile test. So if we're dealing with a tensile test here, we have a specimen, probably a dog bone of some sort, with known geometries that we know when we machined those specimens, and also we know by measuring them after the machining as well. We do a pull test, a tension test on those specimens, and when we do that, what we're recording for data, for our raw data within this here, is our force, displacement, and maybe some time. So we know from that, with force and displacement, we can then use that information along with the dimensions of our test specimen in order to calculate our stress and our strain, and that's what we're using to graph there to create our stress-strain curve. So we take that information for the material dimensions, our force and displacement measurements, raw data from our testing, and we use that to create and calculate our stress-strain curves. Now, these stress-strain curves can give us some information related to material property. So one thing that we can get from that stress-strain curve, we can look at slopes and a couple calculations on there. We can get our elastic modulus. We can use relationships to get Poisson's ratio. We can take a look and find strengths related to those stress-strain curves, and then we can discuss and further calculate toughness and ductility by taking a look at some of the information from that data. Another thing that we want to discuss related to materials here are the different types of materials and their characteristic. So if we're dealing with metals, polymers, ceramics, plastics, whatever it may be, they're all going to have different types of characteristics when we're referring to their actual material properties. Now, how do these compare? Is one more brittle, one more ductile? How does it react under these different tests? What are our hardnesses? What are our modular elasticities? And compare between those. And where this becomes important in a design course there is we tie into the next step here, our material selection process. We want to look at all that information from the material types, properties, characteristics, all that information, and then decide, okay, how does this fit my design project, my product that I'm looking to build here? Which of these materials is going to be best? And that's where we need to go through this material selection process to kind of look through, compare and contrast, and decide what works best for our specific application. So there are some standards, and we're talking about doing this testing right here. And this is important. I've run into this many times in a lot of the tests that I've done, especially for when we're creating standards. So I actually worked for a company over in Plattsburgh that makes tiles. So Schluter Systems, I was a contract engineer over there for a little while. And they work with floor tiling and specifically membranes that we were working on, decoupling membranes. So we would do a lot of testing on these various types of machines, and at that point, when I was working over there, there was no ASTM standard. So we were working with some of these societies and some of these different places to create these testing standards for testing decoupling membranes related to flooring tile. That being said, we have a little bit more insight now into how these testing standards are created and why the wording is so technical and so specific and oftentimes hard to understand. When they're creating these standards, they're trying to make them applicable to a very large variety of applications. So within that, a lot of the wording and the specifics that you need to set up during the testing becomes a little bit overbearing, if you will, as you're reading through these. So that's a little preface into these standards. So as you look these and reference these, take a look at it, look them up, realize that the wording is very tricky. You may need to read it 10, 20, 30 times to really understand exactly what they're asking for. So what I've found is very helpful when we're talking about these standard test methods are, one, yeah, definitely go read through these, locate these, and see how they apply to yours, or figure out which one applies to yours and which portion of these standards. Because as you can see here, we have ASTM E8, E8M 09-10, very, very specific ones for different applications. You really got to make sure, one, you pick the right one. But I would reference this, if somebody else has done a test similar to yours and you're not creating your own standard from scratch, then take a look at their testing process and see which standard they utilize when they were running their tests and say, okay, yes, that does apply to mine. Oh, that's slightly different. Maybe I need to go outside and look at a different standard, but at least let you give you a little bit more insight into the actual wording and how to use the application of these different standards. So definitely reference these, and when you're thinking about beginning a test, you can't just blindly go in there and start pulling a tensile test or running a hardness test. There are procedures that need to be followed, and one of the things that we need to consider that these procedures and these standards cover are factors within the testing room or the testing laboratory where you're running these tests. So this is another thing that I ran into that was extremely important when dealing with some of this tests over at the Schluter system, when dealing with these decoupling membranes, is temperature and humidity. So we're talking about things that are very much dependent upon that. I can't get into too much detail with it. It's still an ongoing testing procedure over there. But if you think about tiling on your floor, and there's different types of grout and different types of bonding agents that you're going to be using, some of them are dependent upon temperature and upon humidity in the air. So if we're running these tests here and somebody else is running them in New York and someone else is running them in Germany and all over the world, we need to make sure that all of us have the same test environment that we're utilizing to run these tests. So that becomes very, very important quickly. So having a room where you have very precise climate control, humidity control, is very important for specific type of tests. Now this can apply to other type of tests too. Maybe you're running it on a polymer or a plastic that, you know, at 110 degrees is a lot more ductile than it is at negative 20 degrees, it becomes brittle. Something like that, and you run the test and you have completely different results just because you varied the temperature. Now, why you would have a testing machine in negative 20 degrees, I don't know. But that being said, there still could be subtle differences between 50 degrees and 100 degrees, and maybe even not so subtle differences between those. So you need to make sure you're not just running this in a basement where there really is no temperature control, and sometimes it's really hot and sometimes it's really cold, and you're wondering why your data results vary from when it was the middle of winter to the middle of summer. So things like that are very much, they're very important when you're talking about these testing procedures, and a lot of that is covered, and that's why you have such fine detail and very well-worded descriptions within these standards that need to be followed for your different testing procedures. So speaking of some of these testing procedures, some of the other things that are specified within that are the actual testing samples. Because again, you want to make sure everybody that's running this test, according to these standards, have as much identical as possible within the testing. So you're only testing the one variable, whatever that may be. Maybe it's the material type for tension testing here. You don't want a different size or shape or grip length of your test specimen to be the thing that changes your data. You want it to be actually comparing the materials and not the shape of the test specimens. So we're here, we have this test specimen here. So this is defined by the standard in ASTM E8 or our DC638, again, depending on your testing, what you need to do, which of those actually applies for you there. So this is the general dog bone shape that we've referred to before in the past. And the reason we have this shape that is dictated over here by these dimensions, we'll get into in a second here, is to ensure that the break will occur at this gauge length in the middle right here. So this is your gauge length in here. You want to make sure the break occurs there, not up here at a sharp corner up here. So that's why we have this radius in there like that, to ensure that it breaks in the gauge length there. And we also need to ensure that the grip forces are minimized in the specimen response right there. So we have all these other dimensions as well, our width of our grip right here. We have the length of this defined there. We have our gauge length, the length of this radius right there. All this information for this type right here, specifically this 638-95 type V. So this may be different for different test materials. So that's, again, why it is important that you go back and you reference everything within those standards and make sure, okay, well, I'm not using this type of material. It doesn't fall under this category that's described for this standard, so I need to look at a different standard because this test material is going to require a different size, shape, dimension of a dog bone. Or maybe for the different materials, they require a different rate. So maybe some are moving at 1 inch per minute, where some are moving at 5 inches per minute. Things like that there are, again, going to affect your data results. So reading these, understanding where to even go for these, and even that they exist, is going to be very important. Again, you can't just run in blindly and start pulling out materials and saying, yeah, there's my stress strain curve, that's my modular elasticity, that's the material properties, done. You can't do that. You need to follow these standards. Again, all that information, the climate that you're in, the environment that you're running the tests in, the shape and size of the dog bone specimen, the rates at which you're performing the test, this and plenty of other things all come into play when you talk about running some of these tests. So now that I told you all that and tell you that there's standards that you have to follow, I'm going to break all those rules here for a test that I ran here. Now, the reason I broke this, and the reason you may want to break those rules and not necessarily follow those standards to a T or even at all, is when you're trying to do realistic testing. So as we saw in those previous slides, we discussed standards where you got a very specific dog bone. You're looking at just the material properties of that and that one thing. Well, what if you're looking at a system as a whole and you want to know when that system's going to fail, which part is the weak part of that system, and there. Now, that being said, that I'm breaking all the rules and doing this, this is a prequel leading into those other tests that you're going to be following the standards. So for this specific test right here, I was working with a company that designs ratcheting medical tourniquets, and in general they also sold individual and developed individual ratcheting buckles and ladder straps and attachments as well. So what we wanted to do for this test here is we were looking at a couple different things. So for this particular test, we were looking at this webbing that we're using, and you can see over here on the left, this is a ratcheting military tourniquet right here, medical tourniquet right here, and you can see up here, it's a little bit tough here, we'll zoom in later, are 2 rings. These are coated rings with grip built into them, and the issue was customers were saying that they were experiencing the actual webbing sliding through the rings. And so this is a design project within itself. A lot of factors go into, okay, what forces are we applying on this, what forces, where does it start to slip, and then it goes back to the actual designing of, okay, do I need to change the geometry of these two rings? Does one ring need to be bigger or smaller than the other? How do the diameters of the rings come into play with this? Is there a certain amount of grip or friction that we can provide with a coating on the rings there that prevents slipping up to a certain loads? Do we want to start slipping at a certain load as a safety precaution? All of those type of things are great questions, but where we need to start is, what load do we start seeing slipping at for the current existing one, and is that acceptable? Because maybe we don't need to go any further. Maybe the customer was using this for an application that was not intended to be used for, and we're fine. So that's where these kind of, call them quick and dirty tests right here, when we're talking about tension testing right there, can be very beneficial. You want to go in there and see, okay, what load is this failing at, and is that realistic? So we ran some tensile tests there, and then we also compared a couple different things. We ran we developed a different type of ladder strap head right over here, where rather than having two separate rings that were stitched in, where we had all those factors that we just discussed there, as far as the ring diameters, sizes, sizes compared to each other, and even how tight the stitching is, that really dictate, what force it will slip at. And we get a standard one like this, it's molded in using injection molded, where we have that there, and we have built-in grips that's identical every time. Is that a better option? So we wanted to run these tests. At the same time, I didn't just want to run the test here without the entire system. Yes, I am concerned, and what we're trying to ask ourselves is, what load can we achieve, what maximum load can we achieve before the webbing slips through either the rings, or in this case here, the slots over here on this injection molded ladder strap. But where is the weak point in the entire system? Is that the weak point, or is the buckle going to fail before we see any slipping? Either on the rings or the slots over here. So that's why I ran this as a realistic whole system here, where I have the ladder strap gripped down on the bottom there, and I have the webbing on the top part there, and I'm pulling there. So is the ladder strap going to fail? Is the buckle going to fail before we see slipping of the webbing through either the rings or the slots? So now, after running that test, we realized there's a lot of other tests that we really wanted to run as well, to understand the system as a whole for a variety of applications. Now, we saw in the previous slide, we were running these in pure tension. So in pure tension, when we ran these tests, that's not necessarily realistic. A lot of times, especially with the ratcheting medical tourniquet application, these were going to be around a circumference, a limb, a leg, an arm, something like that. So this would be around something and not perfectly tensile strength. And the way that the buckles were actually designed, there's a curve in the base of the buckles that's meant to go around a curve. So running in that application was not necessarily the most realistic application. So what we wanted to do was take a look at some practical applications. And one application that I specifically was interested in for my company was I was using these on weight belts. So I wanted to run some tests on weight belts here to see, okay, if I'm running this around a circumference of something and then seeing an increase in pressure, what is that maximum pressure that it can handle? So I ran some tensile tests in there, equated it back to pressure, utilizing a couple of different pressure sensors along the way, and then running some realistic testing applications as well, where I'd actually have people using the belt outfitted with the pressure sensors, exerting a force, expanding out, pushing on it with their abdomen, and bracing their core off these belts. And when they did that, I was able to accurately measure what those pressure readings were, and from there I could back into a test like this, where I could say, okay, I'm going to instrument this with a pressure gauge, which we can see down on the bottom of this slide as well. Down here I have a whole pressure gauge system set up right here, where I run this inside of our belt there, so I could see, well, this tension load on this machine here as it's going around the curve is equivalent to this pressure load, and I know that the max pressure load that I could see from a lifter using this is whatever it was, and from there back it out and take a look at then pressure versus displacement here. But what I really wanted to see here first, before I did any correlation between the pressure, was just when did this fail and did it fail. So I used this tensile testing machine here and ran this test up to I actually ran up to 1,000 pounds. That was the max I could run on this here, but the most I needed to when I did that correlation with the actual pressure was I just needed to make sure it didn't fail up to 700 pounds, and that included a safety factor as well. So Shown here is a little bit of a close-up of that testing procedure in this custom testing rig that I built within here. And again, it was really to run the application that I wanted to see for my specific project of that ladder strap around a curve going into these buckles right here. Now, as a side note, in this right here, what I found was this type of buckle had a specific design so that upon impact loading or even very high loads, this has a floating axis right here. So the way this buckle was designed is if you reach a load that could be harmful to somebody, so you can't crank the buckle too tight, or all of a sudden a really high impact load comes on it, it will lift up the locking mechanism inside the buckle and it'll allow the ladder strap to slide back several teeth on the ladder strap and then relock in spot. So you aren't having a failure of any of the material or a failure of the buckle. This is an integrated design within this specific type of buckle with a floating axis on it. Now, this is fantastic in certain applications where you don't want to allow your user to go so tight that they maybe occlude blood flow. So initially when developing my belts, I thought that this was a phenomenal feature because my thought was that my clients, my customers, would want a safety feature like that so that they can't take it to the point where they're actually occluding blood flow when they're wearing their weightlifting belts. Well, after some actual field testing and getting feedback from people utilizing these, I was wrong. My initial assumption as a design engineer that a safety feature like this would be something that would be very valuable. That way no one can actually cut off blood flow while they're lifting. No. Lifters wanted to crank this as tight as they possibly could, and they didn't care. If they cut off blood flow, they cut off blood flow. They wanted that belt never to move, that buckle never to move and skip a teeth. That having it skip a tooth like that and alert them that it was too tight was something they didn't want. If they want it that tight, they're going to have it that tight. So that led me back to the drawing board with this here. And even though under my tensile tests, I went through this and then I double checked what my failure loads were and everything else is fine, that's not what they wanted. So I went back to the drawing board and had to redesign and redevelop a new buckle type for this right here, utilizing a fixed axis rather than a floating axis so it would never release. And at that point there, then I would have to take a look and see now where is my point of failure. Because before with the floating axis, that was, even though it wasn't a failure, that was the point of failure right there, is when a certain load was achieved, or a certain impact, for this case here, was achieved, it would release a couple teeth back and loosen up. That was considered failure for this testing because that's not what my customers wanted. So I had to go back, redesign it, fixed axis, then test it again and see where then is my failure point there. And what we could find from that is that we had two more areas of interest that we found to be the failure points that we wanted to concentrate on. One being where the buckle was riveted at that hole there, and the second being the shape profile of the teeth on the ladder strap seemed to deform after repeated use. So that's where life cycle testing became extremely important in this here, as when we talked about actually doing this over and over again like somebody would do in a gym and using this belt, the tooth profile became very, very important. And along with the tooth profile, the material that this is made of needed to be durable enough and have the correct shape so that repeated use wouldn't deform those teeth and cause slipping. So I talked a little bit about the realistic results of this and doing some actual testing within the gym. So with this here, we can see this is a tension in the belt related to time. So this was a live test. So what I did was I had a user wear the belt and outfitted the belt with pressure sensors inside. Ran the correct formulas and calculations post-processing here to equate that pressure back to the tension. Now, I developed those relationships between pressure and the tension seen on the tensile testing machine by using that same pressure gauge in both situations. So I could see, okay, if I put this pressure gauge in on the tensile testing machine, I take it up to this tension on there, okay, it's this pressure. Then I have these pressure readings from a user doing deadlifts. Now, one of the things I wanted to see with this here is, does the amount of weight that they're actually lifting come into play? Because that's a lot of the times I'd get feedback from customers, well, I'm not sure about this ladder strap. I squat 1,000 pounds, so, you know, that's for, I'm going to need a really strong belt, and you only tested to 700 pounds. Well, squatting or deadlifting 700 pounds is not the same load as a 700 pounds in pure tension on a ladder strap. Just because you're lifting 700 pounds doesn't mean you're pushing out and bracing off the belt 700 pounds. So that's what I want to do as a comparison here. And yes, there is a little bit. If you're just deadlifting 155 pounds right here, yeah, the amount that you're pressing out and applying pressure to that belt right there, we saw a tension, equivalent tension force from that pressure of 330, 340 pounds right there. And it was slightly higher when I went up to a 245 pound deadlift. And then when I went up to a 335 pound deadlift right there, yeah, it went up even higher and I braced even harder. Maybe I tightened the belt a little bit more so I felt more secure. But then when I got up to 405 deadlift, it's actually a little bit less. So again, this is why I tested these up to 700 pounds in that tension testing machine right there, is because I wanted to include a safety factor. And I'm looking at maybe 400 pounds total, no matter how high I went with my deadlift there. So I did this for squats and for deadlifts and everything and compare the results. This is just one example right here. And I wanted to make this as realistic as possible. That's why this bottom axis right here is time. I wanted to see throughout my entire lift when I was actually bracing the most, utilizing the belt the most. And I also wanted to show this, with the belt on the whole time and me not taking it off, putting it on in a different position, things of that nature. I wanted to be a realistic, comparable result right there. So that's what I found is even as I went heavier, yeah, it slightly applied a little bit more pressure onto the belt, but it wasn't a linear. And it wasn't directly related. It wasn't, oh, when I deadlift 155 pounds, I'm seeing 155 pounds of tension in the belt. No. When I deadlifted 155, I saw 330. When I deadlifted 405, I didn't see 405 pounds of pressure from that deadlift there. I saw an increase of maybe 50. I didn't go ahead, even though I've, more than doubled that weight there, I haven't more than doubled the amount of tension that I'm seeing on the belt there. So that was my realistic comparison. This was run with multiple lifters, multiple times, different belts, different ladder straps, and then compared with those tension tests in the lab. So the next thing in the realistic testing that this brought me to was, okay, I've looked at the tension in there, and now I've looked at the buckle itself and decided that that buckle didn't work, so I needed to find a new buckle design to go with a fixed axis rather than that floating axis there. So then I went ahead and spec'd out a bunch of different buckle types. So this was the initial buckle that had the floating axis that I didn't like, whereas these buckles over here all had a fixed axis with different types of release, different types of locking, things like that. And this is one that was just a pure locking buckle that did not have any ratcheting to allow the user to incrementally get that mechanical advantage to tighten their belt. So I tested all of those as well further to go ahead and see what would perform the best for my application. So within this here, a couple different things, and this is where it's important. You're already seeing I'm bouncing around a lot between the different things I want to test. This was not the case when I actually ran the test. I ran it with one buckle and then only varied the ladder strap type. Or once I decided which ladder strap I wanted, I ran it with that one ladder strap and varied the buckles. There's only one variable at a time, so I could isolate each thing as I went along the way in order to do that material selection for which one would be best. So talking about material selection, I need to test out a couple different types of materials and profiles that I wanted to use for the ladder straps for this testing here. So I had a couple different lengths of ladder straps, a couple different tooth profiles of these ladder straps, and two different materials of that right there. So each of these were tested, and these were tested in a very organized fashion to, again, isolate and only change one variable at a time. These were just all the different things that we did test within that and all different combinations of those. So we ended up, when I say that, there was 180 tests in total that we ran at 15 minutes per test. So I ran 45 hours of testing when taking a look at these different buckles and different ladder straps and running these tension tests on those. So this is not, again, something you just run in there, one buckle, one ladder strap, that didn't work or that did work, done. No, I need to run all the different combinations. Does one type of ladder strap and one type of material work better with one type of buckle, and that ladder strap, tooth profile, ladder strap material, and that buckle combination give me the best results? So I'm not only testing individual parts, I'm testing a system as a whole. And I want to define all of those things. Which systems, which parts, which materials make up the components for the best system as a whole for this. And that's why so much different testing needed to be run. Now this is one here that I did do some SolidWorks modeling and did run some finite element analysis on this testing as well to save myself a little bit of time from the actual testing in the lab, or theoretically save myself some time from the practical testing in the lab. And what I found is actually modeling out these to the accuracy needed to run these tests actually took a lot more time than physically going out and running the tests, and being able to include and account for all the things that we talked about at the beginning of this lecture here, where we have temperature, humidity, and all of those type of factors in there aren't anything that were very easy to run on a normal computer without having a supercomputer for these assemblies and systems. So especially as I talked about the assemblies and running the tests on the assemblies within FEA, yes, it is absolutely possible within SOLIDWORKS. One, it takes a lot of time to get that set up correct, do all the individual part modeling, get the system integrated as a whole, set all your constraints correctly for that. But then on top of that, you need to have a computer that's capable of running such a large, complex assembly in finite element analysis. So that's something that you may or may not have access to. So this kind of ties back to the design process. We talked about when a customer comes to you and says, hey, can you do this? And maybe that's what they want to do, is like, hey, could you run me a theoretical model on this system as a whole? And you may think, oh yeah, I know how to do that in SOLIDWORKS. Sure. Well, is your computer capable of doing that in SOLIDWORKS? And what is the associated time for you to actually model all those individual parts, assemble them together, assign the materials, and run that? So do you have the time and the resources to do what your client asked you to? So continuing on with this here, another thing that we talk about in the design process here is this testing protocol and procedure right here. So this is something that's important, even the very beginning phases of the design process. So as you're talking with your client, you're back and forth with them, you want to discuss exactly what you're going to do, what's needed for this. So again, this ties into, you can't run in there and quickly just do one test and be done. You need to run this on multiple, even for each configuration. A minimum, for mine right here, I ran a minimum of 10. I probably should have ran a minimum of 100 to be realistic with this, of each combination. This is something, if you're talking about meeting the standards, that's another thing you need to look at when you're looking at those ASTM standards for these types of tests. How many times do you need to run this to get accurate results, to provide that information? So you definitely don't want to run it once. I ran it, in this case here, you can see the 5 here. I ended up running it 10 times in the end of this here, just because there was instances where the setup wasn't correct, or something was an anomaly that didn't make any sense. I wanted to run more tests to see if I saw it again. So you can see what I have for each of these tests on the left-hand side are the different ladder straps. So I have the stiff 7-inch ladder strap, the soft 7-inch ladder strap, the stiff 11-inch, the soft 11-inch, the stiff 13-inch, and the soft 13-inch. So I have both material types for each length of ladder strap. Now, a thing to note with these ladder straps is 7, 11, and 13, each of these lengths, each had a different tooth profile. So the actual dimensions of and the shape of the teeth and the ladder straps in general were different between all 3 of those as well. So not only was it just the length that was different, but also the other geometry as well. Now for each of these, I ran them with all 6 of these different types of buckles. So I landed with that PR1 buckle, and at that buckle there, that one did not have the mechanical advantage, that just locked in spot, one fixed axis. I ran it with the RB1 buckle right there. That one was the one that had the floating axis there. I ran it with a stainless buckle right here, a stainless steel buckle, and that one had a fixed axis. I also got a couple samples from other companies that make buckles as well and ran it compared to those. And I looked at, the only thing I really was concerned about at this point was this failure load. I just ran it until it failed. What did it fail at for a load? And then how did it fail? That method of failure is what I was interested in. This was just a static test, a slow pull right here, not an impact loading, not realistic, not life cycling. This was just a max load test. I just wanted to see if I pull this slowly at the same rate for all of these combinations, what is the failure load that each one of these combinations has, and then I took these out afterwards and looked at where it failed. Did it slip in the buckle? Did that floating axis release? Did the teeth deform? And it had to very carefully inspect all of that. Now, at the same time, I was also recording force and displacement along the way during these tests. And where that information became important was taking a look at how much these ladder straps stretched before failure occurred. And was that something that's acceptable? So if I have something that's too soft, too elastic of a material, maybe it doesn't fail, maybe it just keeps stretching and stretching, but is that something that a lifter or user is going to be all right with? Are they going to be okay with pushing against that ladder strap and not having the belt brace them and having the belt give a little? They may not want that belt to give at all. So they may want that stiff material right there. And this is where we run into this stiff oftentimes means a brittle material there, and is all of a sudden just going to break and fail. So finding that material, we talk about material selection now in this chapter, in this module. That's very important. This is relating it back to the design process for a request from our client, from our customer here, that they don't want to stretch a lot, but they also cannot have it fail. The catastrophic failure where the ladder strap just snaps like Brittle failure. So we needed to find that combination, the right material. And this took a lot of back and forth, looking at material property sheets, going back and forth with DuPont. These are all injection molded parts, so I had the control over choosing which material I wanted to run in the injection molding process for these ladder straps. But finding the right one was a challenge. Like some of them, like I said, some of the more soft, as I list them here, materials, Hy-Trels, things of that nature were great in that they didn't break, but they deformed. And when they deformed, maybe they deform enough that they actually slip on the locking mechanism of the ladder strap. So do we want a Hy-Trel? Do we want glass-filled nylon? Do we want a PLU? What type of material is going to be the best, and which type of material combination with these different types of buckles and different profiles of the ladder strap is going to give us our best result. So this is why it was 180 individual tests and ended up, and should have probably been even more as we go further, which we did once we've kind of narrowed it down and eliminated a couple of them out of like, absolutely not, that's doesn't work for this reason. I can't have a floating axis. I do need the mechanical advantage. Let's yank those two buckles out of there. 13 inches is just too long. Let's link the 13 inches out of there. Okay, the tooth profile on the 7 is no good. Okay, we're down to the LS1. Now we're just going to take a look at stiff versus soft, and we're only going to look at these three buckles over here, the RB1 stainless and the Eco and the Aries. And those are our three ones we're really going to run some more tests on because we've already eliminated those other ones immediately. We're going to focus and do more intensive testing on these combinations. So now that we've gone through that practical application and understand a little bit more for the design process of why this material selection is so important and why running these tests, whether it's an FEA theoretical analysis of it or if it's an actual practical tension test, hardness test that we're using, let's now get into our calculations we need to run for a lot of this testing and analysis. So the first thing that we're going to talk about here is stress strain, and in particular we're going to talk about engineering stress here. So what is engineering stress? Well, we have right here our stress is equal to our N over our A1, so we have our load over our cross-sectional area there when we're discussing engineering stress. Now with engineering strain, we have down here our epsilon, or our engineering strain, is equal to our deformation, or our delta, over that original length right there, our LO, where our deformation is the length that we're measuring minus our original length, all divided by that original length there. So this is where I talked about in our raw data, when we're running a tension test here, for example, right here, I'm getting load versus displacement. Well, load versus displacement, yes, as it does relate directly to stress and strain, it is not stress and strain. So that's one thing I really do want to urge you to be cautious about, is don't just take that raw data from your load displacement curve and start running your analysis for looking at your modular elasticity and your yield strength on that curve. That is not a stress strain curve. That is a load deflection curve. And even be more careful than that you're not doing load versus time on the bottom that some of these testing equipment puts your raw data out in. So understand what your units are. So this even goes back to, I know we discussed unit analysis with your problem solving. Unit analysis and paying attention to those units when you're actually doing testing is very, very important as well there. So we need to be in stress and strain. So we take that load that we're measuring, and then in this case here, for our stress, it's the load that we're measuring there divided by our cross-sectional area, which is the dimensions that we're looking at for our test specimen piece right there. Now where the deflection comes in, our distance comes in from that raw data for load versus displacement right there. That displacement comes in to calculate our strain right here, where we take the deformation, or that initial length, by how much it actually has moved right there, that displacement right there, divide by the original length right there, and that will give us our strain. And then with this information now, we can create our stress strain curve. So this is our typical stress strain curve. I know we've looked at it a few times before. So we talk about different regions within our stress strain curve right here. So we can see now we have strain on the bottom right here, and we have stress on the y-axis over here. And there's a lot of information that we can get from this stress strain curve. So we can take a look over here and we can say, okay, this slope right here is our modulus of elasticity. So this relates back to a material property. So let's just say we were testing something, we didn't know what material it was, we didn't know the material properties, we wanted to gather that information. This is where we could use the information from our stress strain curve to back out the slope in this elastic region right here, as we're going from 0 down here up to our 0.8 right there. That is our elastic region. We can back out that modular elasticity. Then we can see our yield strength. We can see our ultimate strength right up here at the top right there. And we can see when it fractures right there. And again, this is stress strain, not load versus displacement. So understanding your regions within the stress strain curve, we can get a lot of information about those material properties from this. So again, we take a look at our elastic region. We can see that transition from elastic to plastic, that transition region right here between A and B right there. We can see strain hardening occurring within this at the next region there, and then we can see our necking occurring as we go from our ultimate strength down to fracture right there. And we can see at the end, there's our fracture at the end where it actually fails. Now, one thing that I do want to note when we're looking at this stress strain curve versus one you may see in another textbook, or one if you're referencing things online, or if you're creating your own from one of these testing machines and it gives out different variables and different units. So I know we've talked about, again, our problem solving here, those 4 things that we want to include in our setup page, how we have our variable, our numeric value, our unit, and how it relates to the problem. Well, this is a practical application of why that is important, not just for you as you're referencing back or your grader to understand what you're doing, but also the fact that not everybody is going to use the same variable name in the same units that you may be used to using. So having that system and being in the good habit of writing all 4 of those things down is going to prevent any errors that may occur from somebody else using different notation than you're used to, and making a very simple error at the beginning that can have catastrophic effects. If all of a sudden they're using a different notation, you think they're talking about something else and you plug it in, your results are way off. Or they're using one unit and you're expecting another unit. So that being said, our textbook right here is going to use this notation right here. SE is going to be our elastic limit. SY is going to be our yield strength, and SU is going to be our ultimate strength right here. So SE, our elastic limit, is right here. You can see, so once we reach the end of that linear region right there in our elastic region, where if you apply a load and then unload it, it returns to the same shape with no deformation, that's in the elastic region there. So there's a certain stress rate here that we'll reach, which equates to a certain load right there, where you can unload it and it will return to the same undeformed length right here. So this is our SE, our elastic limit right there. Then we get to our yield strength over here, which is our SY. So we can see it has come over there. And if we unload it there, it does have an offset that comes back to this 0.2% offset right there. So that's our SY, or our yield strength. Then I have our ultimate strength here, which is the highest stress factor that we're seeing on here within all the testing there. And that is our SU for our ultimate strength right there. So again, pay attention to your notation for your variable names right here that they're using and their indices that we're using with these, and make sure that that is something that correlates with what you're using. It's coming from your testing machine, what goes to another textbook, what one of your coworkers or group partners is using as well. So SP is another one right here. This is your proportional limit that they use. This is the stress where the stress strain linearity ends. So again, this is the notation that our textbook is going to be using for proportional limit right there. So we have our variable name and we have how it relates right there. So if this were an actual problem, you'd also include the other 2 factors right there, the numerical value and your units. SE again, that's our elastic limit right there. And this, the practical terms for this right here, this is a stress where the material becomes permanently deformed. So we saw that there. Again, once you load it to that certain point and you go past your elastic limit, it's not going to return to its original shape. And when it's unloaded, it's going to become permanently deformed. Then we have our SY, our yield strength. Now this is a stress where significant plastic deformation occurs, so we can see that clearly in the graph that we showed on the previous slide there. And then we have SU. What is this? The ultimate strength, and what this is the highest stress that's going to be achieved. So these are, again, related to stress strain right here, what you're going to see, some of the key factors, notations you're going to see from our textbook that are utilized on the stress strain curve.